Welcome to AS-Chemistry Paper 2, AQA 2023. Here's Q1. Pause the video, read it, have a go. Okay, I'm going to go through the answers. So for this first one, we're trying to show which reagent we could use and observation to identify each of these compounds in 1.1. So you can see the first compound has CHO as a functional group, that's an aldehyde. The second has got CHOH, so that's an alcohol. So we're looking at an aldehyde and an alcohol. It's like a secondary alcohol and an aldehyde we're looking at. So the reagent we can use with the aldehyde is either Tollen's reagent. Now that's basically silver nitrate dissolved in an ammonia solution. And that will give you a silver mirror, will be the observation on the inside of a test tube. Now we could also, to identify aldehydes, you've got that blue reagent, hopefully you know it. It's very similar to Benedict's solution. It's basically called Fehling's in chemistry, Fehling's solution. And just like Benedict's, it goes brick red or orange precipitate you get formed when you warm it with the aldehyde. So you can go for either of these. Spellings are really important. If you get the spelling wrong, you won't get the mark. Now, what will be the reaction with the alcohol? You can choose either one of these, Tollen's or Fehling's, and you'll get no reaction, and therefore you will not get a visible change, i.e. Fehling's will stay blue and your silver nitrate solution will stay colorless, or your Tollen's. And as I've said again, make sure you get the spelling right. You can see I put a red cross there where the spellings are wrong. So super duper duper. Now for 1.2, we've got another two compounds. What chemical or reagent could you use to distinguish between cyclohexane and cyclohexene? So pause the video, have a go. Okay, so you should know this from GCSE chemistry. Which reagent do we use to tell the difference between alkanes and alkenes? So we can have bromine water, which is orange, sort of a pale orange in color. And that's going to stay orange with an alkane, as there's no reaction unless you have ultraviolet light, and even then it won't go colorless. And then with the cyclohexene, the alkene, it will go orange to colorless. All right, we're going to move on to the final part of the question here. It's 1.3, and this is a difficult relative atomic mass question. Slightly tricky, slightly different. Table 1 gives the precise relative atomic mass, MR, of some organic compounds measured using high-resolution mass spectrometry. We've got a table here. Use the data in the table to find, first of all, the atomic mass of hydrogen and carbon. Give your answer to 4 decimal places. Use the calculated values of the relative atomic mass of carbon and hydrogen to then work out the molecular mass of C6H6. So the table above tells us that C5H12 has an MR of 72.1416, and we know that C5H10 is 70.1260. So all we've got to do is go C5H12 minus C5H10, which leaves 2 hydrogens. So we'll know that 72.1416 minus 70.1260 is equal to the mass of 2 hydrogens, and that is 2.0156. Now, if we want to find the mass of 1 hydrogen, we divide it by 2. We'll find that our first mark, the relative atomic mass of hydrogen, is 1.0078 using this data. So now we need to find the mass of the carbon. Well, C5H10, we're told in the table, is equal to 70.1260. We now need to take away the 10 H's, and we'll be left with just the carbon, 5 carbons. So we want to take away 1.0078 times 10 from the molecular mass. And what we're going to find, which is 10.078, we're going to end up, the 5 carbons are equal to 60.048. So now to find the mass of 1 carbon, we're going to divide that by 5, as there's 5 carbons. And that means that carbon is equal to 12.0096. And now for the final and third mark, the easiest part, because you get an error carried forward on this if you mess the first 2 up, you can at least get this mark. You just do 6 times your carbon answer and 6 times your hydrogen answer. And if it was correct, you do 6 times 12.0096 and 6 times 1.0078. Add them together and you'll get 78.1044. And that is the mass of C6H6. And that's your lot. This is from 2023 AS-Chemistry Paper 2. We're looking at question 2 here. And yeah, let's get into it. Make sure you pause the video after reading the question and having a go before unpausing and watching the walkthrough. All right, this question's about fuels. Crude oil is separated into fractions by fractional distillation. State the meaning of the term fraction in this context. So what do we mean when we're talking about fraction? You might remember from GCSE or from your AS chemistry knowledge, there's different fractions like naphtha, you've got bitumen, you've got diesel, you've got fuel oil. These aren't just one compound. These are a mixture of similar compounds or a mixture of hydrocarbons with similar MRs or similar sized chain lengths. So you've got lots of different compounds, all with very similar MRs or chain lengths, and they're hydrocarbons, and they make up the different fractions. Obviously, they're separated by the fact that they have different boiling points, which are based on their MR or chain length. Anyway, this will score you 1 mark. Now let's move on. 2.2. Petrol for cars contains branched and cyclic alkanes produced by catalytic cracking. Identify the catalyst used in this process. Okay, this is an easy 1 mark question here, and you just got to learn it off by heart. You need zeolite for catalytic cracking. What is zeolite? Zeolite is a compound made of aluminium, silicon, and oxygen, so sometimes known as aluminosilicates, or yeah, aluminosilicates. Easier to just remember zeolite. Well, let's move on to 2.3. Now, for 2.3, the question is that 3-ether-4-methohexane is a branch chain alkane in petrol. Draw the skeletal formula of this alkane. So the first thing to start with here is the word hexane. This is the main chain or the longest chain. So you just want to make sure that you've got 6 carbons. So with the skeletal formula, I like to put dots or C's just to count them up. You can just use your finger and count it up. You should have 6 points, and I have there, so I can remove these C's. So make sure you've got 6 points, which stand for 6 carbons in your main chain. Now I'm going to identify the first side chain. So it's 3-ethyl. So I want to count 3 carbons along. So that's going to come off here. Now I can draw it going this way. I could draw it going that way, but I'm going to stick with the first option. So like that, that's an ethyl group because it then has 2 carbons coming off the side. And then on the 4th carbon, we just want one side chain, which is the methyl. So just one straight line. And that is the skeletal formula for 3-ether-4-methohexane. Right, zinging on to 2.4, just get this into focus. Give the equation for the complete combustion of 3-ether-4-methohexane. Use the molecular formula for 3-ethyl-4-methohexane in your equation. Once again, pause the video and have a go at writing out this combustion equation. You're going to get 1 mark for the correct molecular formula and 1 mark for balancing the equation. Okay, well, we know it's an alkane because of the name. It ends in ANE. We can also work out how many carbons. Hexane would have 6, but it's got a 3-ether and a 4-mether, so it's got 3 extra carbons, so it's C9. Now, you might remember the formula for alkanes. The general formula is CnH2n plus 2. So if it's C9, it's going to be H20. Now, we could have just worked it out by going through the skeletal formula, but easier to work it out like that. So we're going to write the combustion equation, and this is complete combustion, which means we don't get any carbon monoxide formed, we get carbon dioxide formed. And it's when we burn something in oxygen to form carbon dioxide and water. These are very common in AS chemistry, not so common in the full A level, but pretty common for you to have to do one of these. And they're fairly easy, really. So you should be looking to get both marks here. So we get the first mark for the C9H20. But the second mark's for balancing this combustion equation. So you just take the fact that there are 9 C's in the hydrocarbon, and that's going to give you 9 carbon dioxides. And that's always the case in these combustions. And then the fact that we have 20 hydrogens, I'm going to need 10 waters, 10 times H2 to make 20. So now I need to count up the oxygens on the right-hand side. I've got 18 from the 9 carbon dioxides. I've got another 10 from the waters. Add them together, that's 28 oxygen atoms in total. So I'll come back to the left, and with combustion equations, you always balance the oxygen last. And so I'm going to have 14 oxygen molecules. 14 times O2 is going to make 28. And there we go, that's the second mark. Awesome. So let's clear that. Move on to 2.5. Make sure you hit the like, share, subscribe. It really helps with the channel. If you're not hitting the like, guys, that's not very nice. And that makes you a deuterium, iodine, carbon, potassium. And you don't want to be one of them. Okay, 2.5. Carbon dioxide is a product from the combustion of petrol in cars. Carbon dioxide acts as a greenhouse gas when it absorbs infrared radiation. Give one reason why carbon dioxide absorbs infrared radiation. So there's certain type of molecules that are very good at absorbing infrared radiation, and it's when their bonds vibrate. Okay, now what's the reason why we get vibration in a carbon dioxide molecule? Okay, normally a non-polar bond, you don't get so much infrared radiation absorbed. But however, although it's a non-polar molecule because it's symmetrical, it does have a polar bond. So it has a delta positive carbon and a delta negative oxygen. And so they're going to absorb infrared radiation. And the reason why they absorb infrared radiation is because it's a polar bond, 1 mark, and therefore it vibrates 2 marks. And even better if you say, well, it vibrates at the same frequency as infrared radiation, which is why it can absorb infrared radiation. Okay, so the polar bonds vibrate at the same frequency as infrared radiation. But you will just get the mark for saying, hey, it's a polar bond and therefore it vibrates, and that will get you the mark. Make sure you don't call it a polar molecule because it's a linear molecule and the polar bonds cancel each other out overall. So overall, the molecule is not polar, even though the bonds, individual bonds within it are. Okay, let's move on to 2.6. Once again, pause the video, have a read and have a go. Nitrogen monoxide is formed when petrol is burned in cars. State one environmental problem that NO, or nitrogen monoxide, causes. State what is used to remove nitrogen oxide from exhaust gases formed in petrol fuel cars. So the environmental problems, there's like 4 different answers you can give here. Nitrogen oxides, so that's dioxide, trioxide, or monoxide, cause respiratory illness. They cause breathing difficulties, basically. And they also form acid rain. So any of the nitrogen oxides can dissolve in water in clouds, react with the water to form HNO3, aqueous, which is nitric acid, which is acid rain. And they can also form smog and ground level ozone. How do we remove nitrogen monoxide from cars? We remove them with catalytic converters using those precious metals like platinum and stuff. And what happens is it reverses the nitrogen oxides like nitrogen monoxide and converts them back into nitrogen and oxygen like they originally were in the air. Remember, this pollution forms from the heat of hot car engines. So you're just returning them back to being pure nitrogen and oxygen in the air with a catalytic converter. And that will get you 2 marks. Right, 2.7. I think this is the final question. Petrol sold in the UK contains 10% bioethanol. Bioethanol is like alcohol that's made from crops by fermentation and is seen as carbon neutral. State what's meant by the term carbon neutral. So a carbon neutral crop is one because when it photosynthesizes, it absorbs CO2. So 6 molecules of CO2 are absorbed during photosynthesis. And when you do fermentation and combustion, you combine those 2 equations together, you release 6 carbon dioxide. So overall, there's net no overall release of carbon dioxide to the atmosphere. So it's carbon neutral. So if you weigh up the amount of carbon dioxide absorbed by photosynthesis, it's equal exactly to the amount of carbon dioxide released in fermentation and combustion from 1 molecule of glucose. And that's your lot. That's the end of this question. Question 3. Question is about halogenoalkanes with hydroxide ions, their reaction basically. 3.1 outlined the mechanism for the nucleophilic substitution reaction of 1-bromobutane with sodium hydroxide. First thing to do is highlight the key points, make a few notes if you need to, and have a go. So it's telling us we're using hydroxide ions here. It's telling us that it's nucleophilic substitution, and we've got sodium hydroxide. Let's get into this mechanism. So first thing to notice is our main reactant is 1-bromobutane. So let's quickly draw that out. Of course, it's butane and it's got a bromine atom on the first carbon. So just going to put that there for ease. Now I also want to highlight the electrophile. I've got sodium hydroxide, but of course it tells us it's hydroxide ions. And it's not an electrophile, it's a nucleophile. It tells us that with nucleophilic substitution. And this means it has a lone pair of electrons which it can donate. And obviously it's attracted towards positive things. So what's it going to be attracted to here? This is a nucleophile. What's it going to be attracted to in this molecule? Well, the carbon and the hydrogen are similar electronegativity, so not really there. It's going to be attracted here at this carbon, which is delta positive, and the bromine is delta negative. Now, you don't need to use these in mechanisms in AQA, but they're good for your understanding. And this means the lone pair from the hydroxide ion can be donated towards that delta positive carbon atom. Now, I just want to highlight some mistakes people make. Sometimes people draw the arrow and it appears to go towards a bond. A lone pair of electrons would be repelled from a bond, so never draw a arrow to a bond. For instance, to this one or that one, it's going to get you the mark taken off. Make sure it's going to that delta positive carbon. Now, because I've written the delta signs, which we don't need to do in AQA, this can make it hard for the examiner to see where it's going. So I should really be aware of that as well. I'm better off drawing this arrow going directly to that carbon from the lone pair, so the examiner is in no doubt of where I believe those electrons are going. I'm going to put the delta positive carbon sign down here. Good for our understanding of why the lone pair goes there. Now, I also need to show carbon is in group 4. It has 4 electrons in the outer shell, maximum 4 bonds. This would give it 5 bonds. One of the bonds has to go. It's going to be this bromine bond. So we draw the curly arrow from the bond because the pair of electrons in the bond are going to come out and go to the bromine. And that means our bromine is going to then have a lone pair of electrons and, of course, a negative charge. Now, if I needed to, I could show that as well. Now I'm just going to draw out the products here. You don't actually need to draw these out to get the marks. It just wants the mechanism, sort of first bit here. Well, the product, of course, is going to be an alcohol because nucleophilic substitution. And then we're going to have the bromine with the lone pair. And guess what? It's probably going to get together with that sodium ion that got left behind in the first part. But here I'm circling what you actually need to put to get the marks. You don't need to show the sodium ion. You don't need to show the products. And you don't need to show the possibility is that the sodium ions and the bromine ions will get together to form sodium bromide. You don't need to show that. Your 2 marks are gained by the mechanism there. Okay, let's move on to the next part of the question. So a student investigated the rate of nucleophilic substitution of halogenoalkanes with hydroxide ions. Identical concentrations of 1-bromobutane and 1-iodobutane were reacted separately with sodium hydroxide solution under the same conditions. So they've kept all the conditions the same to make it valid. The concentration of halide ions was monitored during each experiment. Figure 1 shows the results. We've got the concentration of the halide ions on the left, which are being released as the bonds are breaking, and we've got the time underneath. So we can see the reaction of iodobutane is higher, the line, than the one with 1-iodobutane. 3.2, state how figure 1 shows that the rate of reaction for 1-iodobutane is faster than the... And for the second mark, state why the rates of reaction are different. Right, well, first of all, we can see that 1-iodobutane is reacting faster. How can we observe that from that graph visually? Well, we can see that it has a steeper line, a higher gradient, so it's breaking down faster, okay? So that's the visual thing that tells us that 1-iodobutane is breaking down faster. Now, state why this is happening. Well, if we look at the 2 bonds, we've got the carbon iodine bond and the carbon bromine bond in these haloalkanes or halogenoalkanes. And the reason some people think, oh, well, the bromine's more electronegative, is going to mean that you've got a stronger delta positive on the carbon. It's more likely to be attacked by a nucleophile. Well, actually, what it really comes down to is the bond enthalpy, and the carbon iodine bond has a lower bond enthalpy than the carbon bromine bond, so it requires less energy to break, i.e. it breaks more easily, or the carbon iodine bond is weaker. Best answer is to say that the CI bond has a lower bond enthalpy than the CBr bond, so it's more easily broken. Thanks for watching, guys. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you in the next video. Okay, it's for A-level chemistry. Let's get into it. So, 1-methocyclohexene and limonene are cyclic alkenes with a citrus smell. That means they smell orangey or lemony. 1-methocyclohexene is manufactured and used in the chemical industry, whereas limonene is found naturally in orange peel. Here we have the skeletal structure of both of these compounds. 1-methocyclohexene reacts with HBr to form 2 structural isomers. The major product is 1-bromo-1-methocyclohexane. Name and outline the mechanism for the formation of this major product. So essentially, both these molecules, or the one we're dealing with, 1-methocyclohexene here, is attacked by HBr. And of course, that's slightly polar, so the hydrogen's delta positive, the bromine is delta negative, and this is what allows it to attack this compound. So let's have a little look at the mechanism. So first of all, I'm drawing out the 1-mether cyclohexene, which has this double bond here, which is an electron-rich area of high electron density. So it's obviously an area that comes under attack. Now, people might make this mistake, and that is that the hydrogen being delta positive will attack the double bond, the area of electron density. Of course, we know that positive charge protons don't move. It's the electrons that move, and the electrons are not going to move towards the double bond. What we're going to find is the electrons are going to move from the double bond and attack the delta positive hydrogen. So let's redraw that. And this is the correct start to the mechanism. Although I have to say that double bond is a little bit wonky. So what goes on here? Super. So what happens here is the pair of electrons from the double bond actually move out and attack the delta positive hydrogen. So that's your first mark. And we're going to call this M2 because M1 is the mark for the name of the mechanism. So what's the second mark? Well, hydrogen's basically a group 1 element. It can only have one bond at a time. So it can't have two bonds. So I need to break the hydrogen bond to the bromine if it's to form a bond with the cyclohexene. So that's our second mark here, which I've written M3 for. Now, this is going to form a carbocation, and there's two choices to the carbocation. You can see here the hydrogen has joined over here, and this is for the major product, leaving the positive carbon atom in this position. And this is the more likely position for the positive carbon atom, and we'll go into the reasons for that in the next part of the question. And so we're going to look at the name of the mechanism. Well, because originally our delta positive hydrogen attacked this region of electron density, the double bond, this is electrophilic, and it's addition because the molecule is gaining atoms overall. Its mass is increasing, and that's going to get you the 5 marks, one for the positive carbon, one for the bromine with the lone pair and the negative charge. Okay, and one for the name of the mechanism. Right, 4.2, draw the skeletal formula of the minor product formed in the reaction in question 4.1. Explain what the products formed are formed in different amounts. So now we're going to look at the other option. What's the minor product? Well, the less likely carbocation to form is going to be one where you've got your methyl group at the top here, which we don't need to show in skeletal, but it's going to be one where the positive carbon is over here and doesn't have the methyl group attached. That's less likely to form because it will be less thermodynamically stable. So this is the option that happens when we get the minor product. The bromine ion is going to attack this positive carbon here on the other side of the double bond, but it's much less likely to form. Now, we're actually asked just to draw the skeletal formula, so we just want to attach the bromine here, and that is it. That's the skeletal formula there on the right, and that's worth 1 mark. Okay, but that's the minor carbocation, or the less likely carbocation that forms. Now, why is that carbocation less likely to form than the one in the major product? Well, in product 1, or the major product, the positive carbon atom has more alkyl groups attached, and the alkyl group we're referring to is that CH3, that methyl group at the top. Okay, and that's attached directly to the positive carbon in the major group, in the major product, and so it stabilizes the carbocation, meaning that route is much more likely for the reaction to take, as the alkyl groups are electron releasing. Some people call them electron feeding or electron donating. So they donate electrons to that positive carbon atom, and they make it more stable basically, and more likely to form. However, this product that I've shown here, this is the minor product, and this is less stable. The reason why it's less stable is because that, where I've put the plus there, that carbon atom doesn't have any alkyl groups attached. So it is less likely to form because this carbocation would be less stable. So this is why this one is less likely to form. Now, for those people that are interested in the latest research on alkyl groups, which is certainly contradicts everything that we learn about them in A-level, I'm going to put a link in the description, and you can check out some of the latest research that's come out on alkyl groups, which turns up the A-level knowledge on its head. But I wouldn't do that if you don't want to get confused. But if you're interested, go for it. Right, let's move on to the next part of the question. Okay, so let's look at 4.3. Draw the structure of the major product when an excess of hydrogen bromide or HBr reacts with limonene. Okay, so limonene is the second structure we were given in the stem of the question. Which looks like 1-methocyclohexene, but it's just got a couple of extra groups on the bottom. So let's draw that out and then look at what the major product could possibly be. So first of all, we draw out the part of the molecule that's the same as 1-methocyclohexene over here with the double bond here. And then down below, we've got a second double bond coming off at the bottom of the molecule. And this is the limonene structure. So the fact that they've asked us for the major product means they want the one where we get the most stable carbocation formed. And the HBr is going to attack both double bonds. We're going to have addition across both. Why? They've hinted at that by saying there's excess hydrogen bromide. So there's enough to attack all the double bonds. Now, you've got to remember that we've got R groups. Although we don't normally label them, we have alkyl groups. When we're drawing skeletal formula, we just draw them as lines, but they can be methyl or ethyl groups. So the type of carbocations are going to form are these ones where the positive carbon atom is next to the alkyl group. And that's because the alkyl groups are electron donating and they're going to stabilize that positive carbon atom, making that version of the carbocation more likely to form. And so the bromine, our bromine ion, is much more likely to attack that positive carbon atom. And so the bromine is going to appear next to each of those R groups. So when you draw the skeletal formula of the major product, you just want to attach those haloalkanes, you just want to attach that halide ion, to where the R groups are. So our Br is going to attack and attach at these 2 points. Now, the Br is not going to attach at the end of this double bond because that would be less stable, that positive carbon atom to form there. So as it forms here next to an R group, that's where your Br is likely to be. So you need to learn that. 5 or 5.1, a student is provided with 0.03 mole of a sample of an alcohol. The student decides to identify the alcohol using an experiment to determine the enthalpy of combustion. Figure 2 shows the apparatus used. We've got 0.250 kilogram of water, that's the mass. We've got a temperature increase of that water from 18.9 to 17.1. And we're using the specific heat capacity of water, which is 4.18 joules per gram per Kelvin. And we can use this equation, Q equals mc delta T, where the Q is the energy transferred and the delta T is the temperature change. Let's work out the enthalpy of combustion in kilojoules per mole. So we need to do the mass times the specific heat capacity times the temperature increase. Now the mass is in grams, so you need to convert the 0.250 kilograms to grams, so times by 1,000. So you've got 250 times 4.18 times 59.2, and that's going to give you 61,864 joules. That is your energy transfer, but that is in joules. Now you can see our answer is supposed to be in kilojoules per mole. So we need to divide by 1,000, 61,864, and that will give us 61.864 kilojoules of energy was transferred into the water. Now, our final answer needs to be in kilojoules per mole, or mole to the -1, which means we've got to divide kilojoules by moles. And we're given the moles this time, 0.03 moles. Sometimes they give you the mass in grams of the fuel, and you have to convert that into moles using the MR of the fuel. This time we haven't had that extra step. It's only 3 marks. So you just do the kilojoules divided by the moles, and we get 2,062. Now, because this is a temperature increase, this means it's exothermic. Energy has been released to the surroundings. So we would have a negative symbol for our enthalpy of combustion. So you'll need to put minus 2062. You can always do the 18.9 minus 78.1 so that the temperature you receive here for M1 is minus 59.2 as the temperature change. But I just like to look at the question and see if it's exothermic. I stick a negative symbol. Okay, Let's go into 5.2. Table 2 shows the enthalpies of combustion of some alcohols. So we've got ethanol, propan 1-ol, and butan 1-ol, and we've got the enthalpy of combustion in kilojoule per mole to the -1. Explain how your answer to question 5.1 suggests that the alcohol is butan 1-ol. If you've been unable to obtain an answer for question 5.1, assume the answer is minus 2,120 kilojoule per mole. Okay, we actually got an answer. The correct answer from 5.1 was minus 2,064 kilojoules per mole. And at first glance, you'd look at propan 1-ol and go, if I had to choose which alcohol this is, well, propan 1-ol's result was minus 2021. Surely that's closer, and surely that means that the alcohol that we just burnt is probably propan 1-ol, right? Well, actually, that would be incorrect. And the reason is when you do calorimetry, you will always get an undervaluation. Your answer will be less exothermic than it should be. So although we got minus 2064, it should actually have been a bigger number than minus 2064, like minus 2400 or something like that. Or in this case, butan 1-ol, which is the likely answer, minus 2676. So you're always going to lose some heat to the surroundings through the glass and into the air when you do calorimetry. And also, some of the butan 1-ol may not have undergone complete combustion, and incomplete combustion produces less heat. It's less exothermic. So your answer will always be less exothermic than the real true answer. So if that means that our answer of minus 2064 is less exothermic than the real answer, then it can't be propan 1-ol. Okay? It can't be propan 1-ol because our answer is more exothermic than the true answer for propan 1-ol. How did we gain extra heat when we're losing heat? So that's the reason why the most likely identity of our alcohol is butan 1-ol. And the reason that the answers are not identical is because it looks like we've lost almost 612, something like that, 612 joules, or kilojoules, sorry, per mole to the surroundings, or via incomplete combustion. And so that's the answer for 5.2 and explains why we've got an undervaluation or a less exothermic answer, which is what you get with calorimetry. Okay, we're now moving on to 5.3. The equation for the complete combustion of gaseous pentan 1-ol is shown. You have the equation here, written in all its glory, with an enthalpy of minus 3,388 kilojoules per mole, or minus 3,388. We have a table of the bond enthalpies, and it says use the data from table 3 to calculate a value for the mean carbon-carbon bond enthalpy in pentan 1-ol. So you've done these before. You're simply going to work out the total mean bond enthalpy of the reactants minus the total mean bond enthalpy of the products equals the enthalpy change for the reaction. And then you need to solve it to find out what the CC bond is. So I'm drawing out the pentan 1-ol in order to count the number of bonds. So it looks like I've got 4 CC bonds that are unknown. And I have like 11 CH bonds. So I need to do 11 times 412. I need to do 1 times CO and 1 times OH. And then there's 7.5 oxygens. I've also got to do 7.5 times 496. And if you smash that all into the calculator, you're going to get 9075 kilojoules. So on the left-hand side, or the reactant side, we have 9,075 kilojoules. Now I need to add up the products, and I've got 5 carbon dioxide. So how many COO bonds are there? They're worth 805 each, you can see in the table. And what have we got here? So 805, I need to times that by 10, so that's going to be 8,050. Why do I need to times by 10? There's 2 C double bondo in the carbon dioxide. You get what I mean? And then the H2O, a water molecule has 2 OH bonds. So as there's 6 water molecules, there's going to be 12 times 463. And if I smash that all together, I'm going to get a total bond enthalpy of 13,606 for the product side. Now, if we do the reactants minus the products, you get the overall energy change, which is minus 3,388, which they've given us. So we now need to just solve this to find the CC bond. So first of all, let's add 13,606 to both sides to get rid of the minus 13,606. And that leaves us with 4cc plus 9075 is equal to 10,218. Now I want to get rid of the 9075 to leave the CC bonds on their own. So I'm going to minus 9075 from each side. And that will get rid of the 9075 on the left. And it's going to reduce my right-hand side as well. So this ends up with the 4cc bonds equaling 1143. Now I want to find out the value of just one carbon-carbon bond, so I'm going to divide by 4 and I'm going to get 285.8. You can round that to 286, but they'll give you the mark for 285.8 or 285.75, whatever it comes up in your calculator. You'll get the marks for that. And there we go. Lovely jubbly. There's quite a few points here where you could have picked up a mark in the working out. Okay, let's move on. 5.4, this is the final part to the question. The energy stored in this fuel can be compared using energy density values, and they're measured in kilojoule per dm to the minus 3. Okay, so the amount of energy per decimeter. Calculate the energy density of butane 1-ol. So we need to calculate how many kilojoules are in 1 decimeter of butane 1-ol. Well, we know the enthalpy of combustion is minus 2676, and we've been given the mass, the density, which contains the mass 0.810 kilograms in 1 decimeter, and we've been given the MR. And even if you're baffed by this question, the moment you see MR, you should be thinking M mass over MR times moles. Now we know that in 1 decimeter there's 810 grams because we do 0.810 kilograms times 1,000, and we know that we've been given the MR of 74, so I'm just going to do mass over the MR, and that's going to give me the moles, and that means there are 10.95 moles in 1 decimeter. I now need to work out how much energy is stored in 10.95 moles. Well, I've been told the kilojoule per mole is minus 2676, so I just need to times that by 10.95 to find the total amount of energy stored in 10.95 moles, which is the amount of energy in a decimeter, and I'm going to get 29,291. You could write minus 29,291 if you want. Sharing's caring, people. Hit the like, punch the bell, subscribe. Let's get to the marks. Questions about intermolecular forces in some organic compounds. Table 4 gives us some information about 3 organic compounds. We got their boiling points and the polarity of the molecules. State why the CCl bonds in dichloromethane and tetrachloromethane are polar. Why don't you pause the video, have a go at the question, and then watch the walkthrough. So for 6.1, it says state why the carbon-chlorine bonds in dichloromethane and tetrachloromethane are polar. The reason is there's a difference in the electronegativity, the ability to withdraw electrons or pull electrons towards yourself. There's a difference in the electronegativity of the two atoms. And in fact, chlorine is a lot more electronegative than carbon. So it becomes delta negative and the carbon becomes delta positive. And that's why we describe the bond as polar. Now for 6.2, the question says, suggest why tetrachloromethane molecules are non-polar. So that's the middle one in the table there, tetrachloromethane. What you'll find with tetrachloromethane is although it contains 4 polar bonds with the delta negative chlorine and the delta positive carbon, the electronegative chlorines and the carbons are symmetrical and evenly spread out. And so the charges cancel each other out. So there's no overall polarity on that molecule. It is a non-polar molecule. And that is down to the charges cancelling out. Now we're going to move on to 6.3. So once again, pause the video and have a go. Explain why tetrachloromethane is a higher boiling point than dichloromethane. So tetrachloromethane, again, it's got these chlorine atoms that are delta negative and the carbon is delta positive. However, the charges cancel out. It's non-polar. But it's actually got a larger MR than dichloromethane, which means it has more electrons, a larger electron cloud than dichloromethane. And that's because dichloromethane contains 2 hydrogens instead of 2 chlorines, which it would if it was tetrachloromethane. So the tetrachloromethane being a bigger molecule with more electrons or having a larger MR means that it has stronger van der Waals forces. Now, the forces between the molecules are van der Waals forces, or temporary dipole-dipole forces, and these are stronger than the permanent dipole forces that are found in the dichloromethane, purely due to the size of the molecule. Now, the dipole-dipole forces alone, if you were to compare one dipole-dipole force to a van der Waals force, a dipole-dipole force is a slightly stronger intermolecular force. But due to the fact that the tetrachloromethane is so much bigger than the dichloromethane, the van der Waals forces in tetrachloromethane are stronger than the dipole-dipole forces in dichloromethane. And that's due to the amount of the van der Waals forces. Okay, cool. So now we're going to move on to 6.4. This is the last part of the question. Let's just get this into focus. 6.4. Propan 1-ol has a higher boiling point than the other two compounds because of hydrogen bonding. Describe hydrogen bonding in propan 1-ol. So you can have hydrogen bonding if you contain a hydrogen atom which is bonded to either oxygen, fluorine, or nitrogen. Hydrogen to fluorine, hydrogen bonding is the strongest, then hydrogen to oxygen, then hydrogen to nitrogen, like you find in amino acids or proteins. Okay, well, propan 1-ol contains the OH bond, and you just need to describe what is a hydrogen bond here. So I'm using the molecule, the rest of the chain as an R, and then we've got the OH. We've got the delta positive hydrogen atom. The hydrogen bond forms between the delta positive hydrogen on one alcohol molecule and the lone pair on the oxygen of an adjacent, neighboring, or another alcohol molecule. So hydrogen bonding forms between two alcohol molecules, or many more than that, alcohol molecules, but in between two molecules, and it's between the delta positive hydrogen on one and the lone pair of electrons on the oxygen on another alcohol. Cool. And that's what gives propan 1-ol the highest boiling point out of these ones. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. It's about the preparation of an alkene from an alcohol. So we've got 2,3,3-trimethylbutanene. We're making it from 2,3,3-trimethylbutanol. Once again, pause the video, have a read through all the information, then unpause and watch the walkthrough. All right. Let's get into this. So the preparation is done by heating the alcohol, that's the 2,3,3-trimethylbutanol on the left, with the concentrated phosphoric acid that acts as a catalyst, and you get a kind of dehydration reaction and you form 2,3,3-trimethylbutanene, which is an alkene. Now we've got the distillation equipment. So how we separate out our reactant from our product. We've got the alcohol and the phosphoric acid and anti-bumping granules in here. And we've got water in at the bottom, we've got water out at the top, and we've got the Liebig condenser there. And of course, the vapors condense down there to form 2,3,3-trimethylbutanene. The distillate's collected in the range of 77 to 82. And the question is, explain why the water should enter the condenser at the bottom and not at the top. So let's take a little close look at this diagram. Water comes in at the bottom when you're doing distillation, and the water goes out at the top. Now, why is that? Think about the hot vapor is moving down the inside of the condenser, and the cold water is going to move in the opposite direction, a bit like the countercurrent flow mechanism in a fish gill. If you're an A-level biologist, this ensures maximum efficiency of heat transfer between the hot vapor and the cold water. Basically, the hot vapor is always passing fresh cold water, so you've got a bigger temperature gradient and more heat transfer. So also, the water filling in from the bottom ensures that the condenser completely fills with water, because it pushes the water all the way up to the top. So we want to say ensures the condenser fills completely with water, maximizes the efficiency of heat transfer as another mark, or maximizes, yeah, that's fine, the efficiency of heat transfer between the water and the vapor. And this ensures that all of the vapor condenses. Now, why do we want that? We don't want any of the vapor not to condense and to escape, because then we won't get all of our product. Okay, 7.1. Name the complete mechanism for this reaction. We got this reaction here where you can see there's a hydrogen ion from the phosphoric acid, and it's going to the alcohol, and it is the lone pair from the hydroxy group on the alcohol is being donated towards the hydrogen ion from our phosphoric acid catalyst. So can you complete this mechanism? Pause the video, have a go. Okay, I'm going to go through it. I'll do the name afterwards. It's easier to talk about the name afterwards. of the mechanism. It's always easier to draw out the mechanism first. So what we have first of all is a bond forming between the OH group and the hydrogen ion. That leaves 3 bonds around oxygen. You get an oxonium ion. When you get an oxygen atom with 3 bonds, it becomes like an oxonium ion. So you put a little plus on the oxygen. Now this is unstable. So in order to stabilize, and that's going to get you the mark called M2 in the mark scheme, out the 4 marks. Now in order to stabilize this, the bond here between the carbon and oxygen is going to break and donate the electrons to that positive charge on the oxygen atom in order to stabilize it. And that is your M3. So another mark you get for the mechanism. Now you can actually combine these 2 drawings. I'm going to draw it out again to make it a bit easier, but you can combine the 2 drawings to get all 3 of the mechanism marks. So what happens now? We've lost our water and we've just got that CH2 left behind. But the CH2, because it lost the pair of electrons to the oxygen atom, it's now positive, the carbon there. So what happens is a hydrogen atom breaks off and donates its electrons to stabilize it, and we get a double bond forming. You can actually combine these and put these both on the original drawing, which I'll show you now by adding in. So to the original drawing, I've added a little blue arrow and a plus if you wanted to combine and not do it as 2 separate drawings, but I prefer the 2 separate drawings, but you could combine all in one, as I just showed you there. Now, what you can see, that will get you M4. We could have added that in over here on the original drawing. And you might notice that water is being eliminated. So what's the name of the mechanism of this reaction? It's an elimination mechanism. So we just call this elimination, and it's purely because the water is being eliminated. Notice that hydrogen ion that breaks off in the second part of the reaction shows that the phosphoric acid is a catalyst because we're reforming that hydrogen ion from the phosphoric acid. And so the name of the mechanism is elimination, and that's your M1 mark. So that's how to get the M1, M2, M3, M4 marks. 3 for the drawings, 1 for the name, which I always do the name afterwards because you'll find a clue to whether it's substitution, elimination, or addition from the drawings. Now, I'm drawing the final product here, the alkene. You do not get any marks for drawing the final product. They assume you could work that out easy peasy, not worth a mark. So then we've got our double bond and lovely jubbly. That's what the final product would look like. It's an elimination reaction, dehydration. We've removed water. And there we go. Right, let's move on to 7.3. In a similar experiment, 12 centimeter cubed of 2,3,3-trimethyl-bute-1-ol, MR116, produces 6.12 grams of 2,3,3-trimethyl-bute-1-ene, an alkene. Calculate the percentage yield. The density of 2,3,3-trimethyl-bute-1-ol is 0.818 gram per centimeter cubed. So we've been given density, which means we're probably going to use the density calculation. And we've also been given the MR. And we've been given a volume, but we haven't been given concentration. So we're probably not going to do N over CV. And we've been given percentage yield, so we're going to need that. So you're going to need several calculations here. One of them is definitely going to be mass over density times volume. You should know that off by heart. When you're given density, you'll normally have to do that. And then we're going to also have, oh gosh, I put moles over MR. I meant to do mass over MR, or Mr. Moles with mass at the top. You get the idea. Yeah, M over MR times moles. Probably the most common equation in the whole of A-level chemistry, that second triangle I've drawn there. We'll have a quick look at the reaction. Let's whip to the reaction. It's a 1-to-1. Look, the alcohol to the alkene's 1-to-1. That might be, we might need that in this equation as it's a moles one. You generally need to know ratios. So let's go through and zoom out a little here to give ourselves some working space, and let's go through and crack this final part to the question. So let's use the density first of all. So we've been given the volume of the reactant, which is the alcohol, and we've also been given the density of the alcohol. Remember, it's an alcohol becoming an alkene. So we've been given the volume and the density of the reactant alcohol. So what we can do, we can use that density and that volume. 12 centimeter cubed is the density, times it by the volume. That's why you have to know this equation off by heart. 0.818 times 12, and that is going to give us our mass of our reactant alcohol that we are actually starting with. And that works out as 9.816 grams. So that's going to score you your first mark for working out the mass of the alcohol that we've got at the start. Now we can work out the moles of alcohol that we've got. We know that we've got 9.816. We've been given the MR is 116. And so we can actually work out the moles of the alcohol that we've got if we wanted to. Now, remember that percentage yield, we're going to need this for the final part of the calculation, is the actual mass over the expected or maximum theoretical mass. So you can either call it expected mass or maximum theoretical mass. Well, we know what the mass of the alcohol is. That's neither our actual or theoretical mass, but it does allow us to work out the moles of the alcohol, and then we know it was a one-to-one reaction. So by working out the moles of alcohol, we know what moles of alkene of 2,3,3-trimethobutan-1-ol we should produce. Awesome. So do 9.816 grams, which is the mass, over the MR of 116, and this will give us our moles of alcohol that we expect to make, and that's 0.0846. That's our moles of alcohol. Now we know it's a one-to-one reaction, so that's the moles of alcohol used. As it's a one-to-one ratio, I'm expecting us to make 0.0846 of the alkene. When we dehydrate it with the phosphoric acid, we eliminate the water as we did above in the mechanism earlier, we should make 0.0846 moles of the alkene. Now all we need to do is work out the MR of the alkene, and we can do the MR times the moles, and we can find out what our expected theoretical maximum mass of alkene we should have produced. So let's do that now by doing the MR times the moles. Now the moles is 0.0846. Now we need to work out the MR. Well, the formula of the alkene, as it is 2,3,3 trimethyl, so it's got three methyl groups, that's three carbons, and bute, and it's an ene. That means there's 7 carbons, C7. Remember the formula for alkenes is CnH2n, so just double the number of hydrogens. So C7H14, which has a 98 MR. So our alkene has an MR of 98, so times that by the number of moles we should make, and it tells us that the expected mass is 8.29 grams. So what did we actually get? We actually got 6.12 grams. We should have got 8.29 grams. So we do 6.12 divided by 829 times 100. Bob's your uncle, Fanny's your aunt, 73.8%. Boom! There we go. And that's for our 5 marks. So we'd have got M1 here of the 5 marks for working out the mass of alcohol reactant we started with, basically solving the density equation. Then converting that into moles of alcohol would be M2. The ratio is 1-to-1, so that's also our moles of product. And from there, you can work out the MR, the expected mass, and the percentage yield. All right, guys, draw the Maxwell-Boltzmann distribution curves for a fixed mass of a gas at 2 different temperatures. This gas decomposes when heated. By reference to these distribution curves, explain why the rate of decomposition of this gas increases at higher temperatures. And this is a whopping 6 marker. So once again, pause the video and have a go. Okay, so the first thing that I would do is highlight some of the key bits so I can work out roughly what the breakdown to this 6 marks is. So I need to draw some Maxwell distribution curves at 2 different temperatures, and that's going to be worth up to 4 marks. So can you draw the axes? Can you label the axes? Can you draw a curve for 2 different temperatures, say 10 and 20 degrees or 20 and 30 degrees, a low temp and a high temp? And that will get you up to 4 marks. And then for the last 2 marks, can you explain why the rate of decomposition of this gas increases at higher temperatures? i.e., why does the rate of reaction increase at higher temperatures? So let's get on and draw this graph. So we need to draw a y and x axis. On the y axis, you normally have number of molecules. And on the x-axis, on a Maxwell-Boltzmann distribution, you have the kinetic energy. I'm just going to label it energy because I'm lazy. But you could label it kinetic energy if you want to. Now we need to draw a curve. And your curve should start at about 0 energy and 0 number of molecules. And it should go like this. This is our first temperature. We don't want to go right down to the bottom, so we leave a little gap. And now I'm going to use a different color. Obviously, you might not be able to in an exam. And for a higher temperature, there's 2 things you need to do. You need to draw your curve to the right. Notice my curve is shifted to the right. The area under your lower temperature, black curve and the red curve, the area should be roughly equal visually to look at. So this red one is my higher temperature and the black one is my lower temperature. The area under them should be roughly equal. Now you can put a temperature if you want, 20 and 30 degrees, as long as the examiner knows, one is high, one is low. There should only be one point where they cross. So if you've crossed these lines at more than one point, you won't get the marks for that. So that's really going to pick you up labeling the axes, having the lower temperature curve drawn correctly and the higher temperature curve is 2 marks. Only having them cross at one point is 3 marks. And then labeling the activation energy. So any molecules beyond this dotted line have energy above the activation energy. And what we can see as we increase the temperature, you get a greater number of molecules or greater proportion of the molecules have energy above the activation energy. But your number of molecules is roughly equal. If you added the area of both curves, it would be equal. So really, you've just increased the kinetic energy of the particles at a higher temperature. So your explanation for marks 5 and 6, you'll get 4 marks for the graphs. So for 5 and 6, we want to explain why the higher temperature, the molecules at a higher temperature decompose at a faster rate, basically. Well, we need to state that they have more kinetic energy. And so there are more molecules at the higher temperature that have energy or kinetic energy above the activation energy. We also get more frequent collisions. Important to use the word frequent, or more collisions per second. And that means that we're also going to have more successful collisions. So we're going to have a higher proportion of successful collisions because there are more molecules with energy above the activation energy. If the molecules on the left-hand side of the activation energy collide, they don't actually react because they don't have energy above, but we're going to get more successful collisions here. So the final answer, at a higher temperature, this is why the rate of reaction or decomposition is higher. So you need to include that more particles have a higher kinetic energy. It's above the activation energy, so we get more frequent and successful collisions. And that will get you your 6 marks. Once again, hit the like, subscribe. Let's get to the marks. I'll see you in the next video. Okay, time to go through the multiple choice section from the 2023 paper 2 AS-Chemistry for AQA. Just remember, you've got to put a little circle inside the box. If you make a mistake, you put a neat cross through it. Which monomer forms this polymer? So what we've got to do here is essentially, you might be able to just spot this straight off the bat. If you want, I'm going to go through the, pause the video, have a go, and then I'll go through the answers. I'm going to go through each one and show you why they're not the correct one. Okay, so first up we have but1-ene. So it's got a double bond on the first carbon, but1-ene. What's the polymer it's going to make? Well, remember, you just take away the double bond, and around the double bond you put brackets where the double bond used to be, and then you fold everything else underneath. So the CH2, CH3 is going to fold underneath where the double bond was, and that does not match our monomer. So now let's look at but2-ene. Now, this is but2-ene, so the double bond's in the middle, and it's E, entogen, which means opposite. So it's going to have a CH3 group opposite across where the double bond used to be. So CH3 there, and an H and an H. And you can see that doesn't match our monomer. So that's the incorrect answer. Now let's look at Z-but2-ene, and that's basically going to be 2 H's either side of where the double bond used to be and 2 CH3s either side of where the double bond used to be. And again, that's not going to match our monomer. Now looking at the final one, we have methyl propene. So the methyl group has to come off of the middle. Otherwise, if you stick it off of carbon 1 or 3, it's going to end up being butene. So methyl propene, it has to come there. And when we draw this out, we tuck the first CH3 under because the brackets go around the double bond. And when you do that, look, you get a CH3 at the top, which was the methyl from the methyl propene. And the CH3 from the start of the propene gets tucked under, and it does match the monomer in the stem of the question. So the answer here is D. Okay, let's move on to multiple choice question 10. Which equation represents a propagation step in the chlorination of methane? Okay, I don't like these ones with a hydrogen free radical. They're obviously not in the chlorination of methane. Um, Obviously, we should, yeah, let's get rid of A. That's got a hydrogen free radical. We don't like that. Here we've got a chlorine free radical attacking a methane. And again, it's forming a hydrogen free radical. That doesn't happen. So you're really looking at the answer C here. You've got a methyl free radical attacking a chlorine, and it reforms another free radical, so it's propagation. This final step, D, is a termination, so that's not the correct answer. Right, let's go to 11, which is the overall equation for the reaction of CCl2, CH2, CCl3, sorry, with an excess of chlorine and ultraviolet radiation. Notice there are two, that on the CH2, as it's an excess of chlorine, that means you're going to get both hydrogens in the middle there substituted for chlorine. So the only one that fits that description is C. Okay, and it's due to the fact there's an excess of chlorine, so you get both hydrogens substituted. Question 12. Most scientists believe that ozone in the upper atmosphere should not be allowed to become depleted. What's the valid reason? Well, ozone absorbs ultraviolet radiation. It doesn't help prevent global warming, and it doesn't help to remove pollutants such as chloroalkanes. However, it can be used to kill viruses and bacteria, but that's nothing to do with the depletion and why scientists are worried about its depletion in the atmosphere. So the answer is A. Right, question 13, which is not a possible product of the reaction of this compound with potassium hydroxide. Okay, so pause the video and have a go at this one, and then I'll go through the answers. Okay, well, when you have potassium hydroxide, essentially, we're not really looking at the potassium hydroxide. We're looking at the hydroxide ion, which is going to attack. So the potassium ions are really just spectating in this. The hydroxide ion's got its lone pair and its negative sign, and what that's going to do, the lone pair is going to attack that delta positive carbon atom here, and in this situation, if you just use reflux with potassium hydroxide, you're going to get nucleophilic substitution, and the OH minus ion is acting as a nucleophile. And so definitely A is a possibility from nucleophilic substitution. The answer here is B. That's definitely not possible. C and D are possible if you use ethanol and reflux under anhydrous conditions. The hydroxide ion acts as a base and you get elimination. So C and D are possible, but B definitely not. It wasn't connected to the bromine atom. So 14, the infrared spectrum of an organic compound is shown. What compound produces this spectrum? Well, if you look on your data sheet, you'll see you get that broad band there from an OH bond, and you get this really sharp peak at about 16 something or other, which is the double bond. So it's but2 N1ol, however you say that. So it's got the double bond and it's got the OH. Which reaction results in an overall change in the shape around a carbon atom? What you're looking for here, what's going to involve a change around the shape of a carbon atom? Anything with a carbonyl bond, a C double bond O, or anything with an alkene that is got rid of from reactant to product, or from product to reactant changes, you get vice versa. Basically, you go from a planar bond to normal rotation. There's no rotation around these CO bonds. So if you've got a carbonyl group or a carboxylic acid group, or you've got a double bond like an alkene, then you've got no rotation. If you go from that to a normal single bond, you're going to get rotation, and you're going to change the shape. And so what we have with C, the reaction of actually, it's going to be B, polymerization of tetrafluoroethene. And it's because you've got a double bond where there's no rotation. So that's a planar molecule. And then it goes to a single bond where they can rotate, and you basically got a three-dimensional shape going on there. So, yeah, the answer is B. That was a bit of a long-winded way to go through that one. Right. 16. Which statement about the industrial production of ethanol from ethene at 300 degrees is correct? This one's a little bit complicated, but basically an increase in pressure decreases the equilibrium yield of ethanol. So what we have to look at here is There are two gas molecules on the left, there's the reactant, and there's one gas molecule on the right. If you increase the pressure, it's going to move to the side with the least gas molecules. So that means it's going to move, the equilibrium shift will be to the right because that side has the least gas molecules. Le Chatelier says it will do the opposite. You've increased the pressure, it will try and decrease the pressure, and that means we're going to get an increase in the amount of ethanol. So it's definitely not A. That's an incorrect statement. B, an increase in pressure increases the value of Kc. Well, if you change the pressure or concentration, in this case it's pressure because we're dealing with gases, but if you change the pressure or concentration, they do not affect Kc because it's just a ratio and the ratio remains the same. Even if the amounts change on either side, the ratio remains the same. An increase in temperature increases the equilibrium yield of ethanol. Let's check out C. So it's an exothermic reaction shown by the minus sign on the kilojoule per mole. So if I increase the temperature, it's not going to move towards the exothermic side. It's going to move towards the endothermic side, increasing the amount of reactants. So it's going to decrease the yield of ethanol. And then if we look at D, which is the only answer left it can be, and temperature can affect Kc. An increase in temperature affects the value of Kc. Let's see, if we increase the temperature, it's going to shift to the reactant side. Oh no, sorry, an increase in temperature decreases the value of Kc. That sounds right. And the reason is because it's exothermic, we're going to shift to the reactant side, and that is going to decrease Kc. Imagine you were 5/2, but now you're 5/5, say. So you're going to get a smaller Kc. Instead of being 2.5, Kc is going to go to 1. You're basically, we're doing products over reactants. And if you, in this situation, if you increase the temperature, you're increasing the reactants at the bottom of your division calculation there. And so that's going to reduce the value of Kc. And temperature is the only thing that's going to affect the value of Kc. Concentration and pressure don't. Right. We can zing on. I could do 4/2 is 2, whatever. Yeah. Doesn't really matter. You get the idea. Anywho, 17. What is the minimum volume in decimeters of air needed to complete? Oh, that's a bit better. Can read a bit better now. Yeah, what is the minimum volume in decimeters of air needed for the complete combustion of 1 decimeter of methane? Assume that air contains 20% oxygen by volume, so only 20% of the air is oxygen. Assume that all volumes are measured at the same temperature and pressure. So what we need to do, that means that decimeters is equal to moles. So if I've got methane plus oxygen goes to carbon dioxide and water, we just need to balance this up. So I need 1 carbon dioxide, but I'm going to need 2 H2O because I need those 4 hydrogens on the methane to be balanced. And that means I've got 4 oxygens on the right, so I need a 2 here. And this tells me the ratio of oxygen to methane is 2:1. So I'm going to need double the amount of oxygen. So if I have 1 decimeter of methane, I'm going to need 2 decimeters of oxygen, right? So you would think the answer is B. For 1 decimeter of methane, I'll need 2 decimeters of oxygen. But remember, it's asking us how much air do we need? How much air do I need to get 2 decimeters of oxygen? Well, only 20% of the air is oxygen, so I'm going to need 10 decimeters of air in order to get 2 decimeters of oxygen to completely react with the methane. So I need 10 decimeters of air. The question wasn't how much oxygen do we need, but how much air do we need? So the answer is D. Superbulous! Right, we're moving on to question 18. Okay, moving on to question 18. Which is the IUPAC name for this compound? Now we've got A, B, C, or D. All of them are hexene because there's 6 carbons, and all of them have a 3 ene, and that is correct as well because the double bond is found on the 3rd carbon. What we need to do is use the Charning-Gold principles to work out high priority and low priority. So fluorine has an atomic number of 9. I go to the carbon on the I go to the group on the opposite side of that carbon atom on the double bond, and it's carbon, which has an atomic number of 6. So fluorine is a high priority. I put HP, and the carbon is a low priority. Then I go to the hydrogen on this side, and it has an atomic number of 1. So carbon, as we've said before, has an atomic number of 6. So this time the high priorities underneath and the low priorities on top. So what we find is the two high priorities are opposite each other. That's entogen. It's not Zasuman. It's not Z. So it's an E isomer. The high priorities and low priorities are across from each other diagonally. So it's like trans or E. It's an E isomer. Now I just need to work out, is it 3-fluorohexene or 4-fluorohexene? Well, we can see the fluorine atom is attached to the third carbon. We give it the lowest numbering possible, and that would mean that it's E3-fluorohex3-ene. So the lowest number we can assign, which is what you do with IUPAC names, to the fluorine is 3. So it is E3-fluorohex3-ene. That's the correct answer for 1 mark. Let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
So methyl propanoic acid is the molecular formula of C4H8O2. Let's simplify that by dividing by 2 and we get C2H4O. Circle that there. That is the correct answer. So the answer here is D. All right, we're zinging on to the last two questions now. So nearly done, people. Stay with it. Question 22, pause the video, have a go, all that jazz. The alcohol over here can be oxidized. CH3, CH2, CH2OH can be oxidized. Which compound cannot be produced by oxidation of this alcohol? So we've got is that butanol? No, that's propanol. Right. If you burn propanol, you're technically oxidizing it. It's combustion, and you're going to release carbon dioxide. So you can make carbon dioxide by adding oxygen to it when you burn it. If you oxidize, this is a primary alcohol. If you oxidize a primary alcohol, using potassium dichromate, you're going to get an aldehyde or a carboxylic acid under reflux, aren't you? So, yeah, the only one you can't do is get a ketone. This is a primary alcohol. A ketone has to come from a secondary alcohol. So the answer that cannot be produced by oxidation of this alcohol is B. You can't make a ketone from a primary alcohol. Well, it's not straightforward anyway. Right. Last question in the paper, 23. What is the atom economy for the formation of ethylamine in this reaction? So remember, for atom economy, you want the useful product over the total product's mass. Okay, now if there are coefficients here, like 2s and 3s in front of these molecules, you do need to include them. So it's not just as simple as using the MRs. You do have to include the total mass. So you do need to include the coefficients. So useful, but there aren't any here, so we don't need to worry about that. So useful products over the total products. So we want to do ethylamine over ethylamine plus whatever the hell that is, ammonium bromide. So there we go. And if you add up all those numbers, CH3 is 15, CH2 is 14, nitrogen's 14, H2. So that is going to be 45, and then we're going to do that over that plus the N is 14, H is 4 plus bromine 143, 45 over 143 times by 100. What do we get? I think we're going to get 31.5%, roughly, once you round it up. There we go. I hope you enjoyed that. Sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you on the next video.
You're still here? It's over.